In this episode, we'll tackle designing a web crawler, a foundational component behind search engines, SEO tools, and data aggregation systems. At a high level, a web crawler starts with a small set of seed URLs and automatically traverses the web by following links on each page it downloads. But once you try to build one at scale, things like duplicate content, server politeness, spam filtering, and distributed crawling all come into play. Designing a web crawler isn't just about fetching pages. It's about doing it efficiently, respectfully, and at scale. In this video, we'll walk through the key system components of a modern web crawler, how to manage the crawling workflow from URL selection to content storage, and deep dive into performance, prioritization, and distributed architecture best practices. Let's dive in. The problem is to design a web crawler that starts by collecting a few web pages seeds and then follows links on those pages to collect new contents. Here are some good requirement questions to ask. How many web pages does the web crawler collect per day? Shall we consider newly added or edited web pages? Do we need to store the pages? How do we handle web pages with duplicate content? Let's walk through the overall architecture of a web crawler, a system designed to automatically browse and collect content from the web. We start with a set of seed URLs, which are our initial starting points for crawling. These are added to the URL frontier, which is a FIFO queue storing all the URLs waiting to be downloaded. The HTML downloader picks URLs from the frontier and coordinates with the DNS resolver to get the IP addresses of the target websites. Once the IP is resolved, it downloads the HTML content of those pages. Downloaded pages are handed off to the content parser, which parses the HTML and checks if the page is valid or malformed. Valid content is then sent to the content scene module, which checks whether this content has already been downloaded. If the content is already known, it's discarded to avoid duplication. If the content is new, it's sent to the content storage module, which archives the HTML for indexing or further analysis. At the same time, the content is passed to the URL extractor, which pulls all the hyperlinks from the HTML. These newly found URLs are then passed through a URL filter, which removes undesirable links such as error pages, mail to links, or non-HTTP URLs. Filtered URLs go through the URL scene module to check whether they have already been visited. If not, they're added back to the URL frontier, and the cycle continues. Additionally, we maintain URL storage to record every URL that has already been visited, ensuring we don't fetch the same page multiple times. This modular, queue-driven workflow allows the crawler to scale efficiently while avoiding redundant downloads and ensuring comprehensive coverage of the web. Let's dive deeper into the design aspects of a web crawler that make it efficient, polite, and scalable. 1. DFS versus BFS. Depth first search, DFS, isn't ideal here. It can follow links too deep into a single domain, leading to inefficient crawling and ignoring broader coverage. Breadth first search, BFS, implemented using a FIFO queue, is more suitable. It helps maintain better domain diversity and coverage, especially early in the crawl. 2. Politeness. We must avoid overwhelming any single server. Implement crawl delay or use host-based rate limiting to ensure that we don't send too many requests to the same server in a short period. 3. Prioritization. URLs in the frontier can be prioritized by factors like page rank, traffic estimates, update frequency. This ensures important or frequently updated content is crawled sooner. 4. Freshness. The web is dynamic. We need to recrawl pages periodically. Use heuristics or change logs, like last modified headers, to decide when to refresh content. 5. URL frontier storage. The frontier can grow very large, so we use a hybrid storage model. Keep hot URLs in memory, cache, for fast access, and overflow to disk for cold ones. 6. Robots.txt compliance. Before crawling a site, we must check its robots.txt file. This file tells us which parts of the site are off limits to crawlers. 7. Spider traps. Malicious or poorly designed sites can generate infinite or near infinite URLs. Custom filters are needed to detect and block these traps, e.g., patterns like calendar pages, session IDs, or recursive paths. 8. Spam filtering. Spam pages should be filtered using content analysis, such as excessive ads, keyword stuffing, or redirect loops to improve crawl quality. 9. Performance optimizations. Distributed crawling. Assign different URL subsets via consistent hashing to different crawler nodes. Cached DNS resolver reduces overhead by caching DNS lookups. Geographic locality. Crawlers located near the target servers reduce latency. Short timeouts. Helps avoid delays from slow or unresponsive servers. Crawler state checkpointing. Saves states periodically so that crawls can resume gracefully after failures. Data validation. Ensure that downloaded content is not corrupted and matches expected MIME types or formats. These deep dive decisions help ensure the crawler remains fast, respectful, reliable, and scalable, all crucial for large-scale web indexing.